Hi friends, today we discussing about the topic Schrodinger equation of central potential. This topic is belongs to our chapter angular momentum. Before going to Schrodinger equation of central potential, we first know that what is central potential. Potential that depends only on the distance with respect to the origin is known as central potential. ഒറിജിനിൽ നിന്നുള്ള ഡിസ്റ്റൻസിനെ ഡിപ്പെൻഡ് ചെയ്യണ പൊട്ടൻഷ്യലാണ് സെൻട്രൽ പൊട്ടൻഷ്യൽ. ഓക്കെ, ജനറൽ പൊട്ടൻഷ്യൽ ദാറ്റ് ഡിപ്പെൻഡ്സ് ഓൺ ആർ തീറ്റ ഫൈ, ബട്ട് ഇൻ കേസ് ഓഫ് സെൻട്രൽ പൊട്ടൻഷ്യൽ ഇറ്റ് ഡിപ്പെൻഡ്സ് ഓൺലി ഓൺ ദി ഡിസ്റ്റൻസ് വിത്ത് റെസ്പെക്ട് ടു ദി ഒറിജിൻ. Central potential is invariant under any rotation because it is independent of theta and phi. So it is invariant under any rotation. In our syllabus, we have to deal from this equation h is equal to p square by 2m plus v of r, where h is the Hamiltonian. We know that Hamiltonian is the sum of kinetic energy and potential energy. P square by 2m term for kinetic energy and V of R term for potential energy. So, the fundamental importance of this Hamiltonian lies in the fact that it is spherically symmetrical. It is spherically symmetrical because in Hamiltonian we use potential term as V of R, that is central potential term. V of R is the central potential term. Classically, we expect orbital angular momentum to be conserved in such a system. This is also true quantum mechanically because it is easy to show that L p square is equal to L x square is equal to 0. LH is equal to L square H is equal to 0. Here we can see some commutation relations. That is, both L and L square commute with Hamiltonian H. Then we can say that if the Hamiltonian involved in a problem is like this, h is equal to p square by 2m plus v of r, we can say that such problems are central potential or central force problem. Here we can see the commutation relations. L p square is equal to L x square is equal to 0. LH is equal to L square H is equal to 0. Put these equation number 2 and 3 respectively. Then we have to move on to topic radial equation. The radial equation. From equation number 3, what was equation number 3? This one was equation number 3. From equation number 3, we can clear that we should search for a energy state. That is, energy state, our energy state ket alpha is equal to ket ELM. We already studied that for the Hamiltonian and L square and for LZ we have the eigenvalues as E, L into L plus 1 h cut square and M h cut. Here Hamiltonian's eigenvalue is E, L square eigenvalue L into L plus 1 h cut square and LZ eigenvalue is M h cut. So we can write H cut ELM is equal to E cut ELM. L square cut ELM is equal to L into L plus 1 h cut square into cut ELM. Similarly, LZ cut ELM is equal to M h cut ELM. Cut ELM. Then we know from hydrogen atom in a spherical polar coordinate system. spherical polar coordinate system. We already studied this equation, hydrogen atom in spherical polar coordinates. That is, our equation is become 1 by r square dou by dou r of r square dou by dou r psi of r theta phi plus 1 by r square sin theta dou by dou theta sin theta into dou by dou phi psi of r theta phi plus 1 by r square sin square theta dou square by dou phi square into psi of r theta phi plus 8 pi m by h into e plus e square by 4 pi epsilon 0 into psi of r theta phi is equal to 0. Then after using variable separable method, we get only in terms of radial part, that is 1 by r square d by dr of r square d by dr REL of r plus 2m h cut square into e minus v of r minus l into l plus 1 by 2m r square into REL of r is equal to 0. We have to study from this equation. We do not have too much more about equation number 4. For electron hydrogen atom in spherical polar system, we have to study only from the radial part. Then after open this bracket, then we get 1 by r square d by dr of r square d by dr REL r minus 2m h cut square into v of r minus 2m h cut square into l plus 1 into h cut square by 2m r square is equal to minus 2m h cut square into e into REL of r. Look, this term is coming from the left hand side. That is, here 2m h cut square into e. When we open this bracket, our first term is 2m h cut square into e. Put this term into the right hand side. So we get minus 2m by h cut square into e. Then this term REL of r is go to right hand side. So we get right hand side is totally minus 2m by h cut square e into REL of r. REL of r. Then after doing this, then multiply all terms by h cut square. Multiply all terms by h cut square by 2m. Then we get minus h cut square by 2m d by dr of r square d by dr plus l into l plus 1 into h cut square by 2m r square plus v of r into REL r is equal to EREL of r. Put REL of r is equal to UEL of r by r. Substitute in the above equation. Put REL of r. Instead of REL of r, we substitute the term UEL of r by r. The r in the term denominator in RHS and LHS get cancelled. So we obtain the last equation minus h cut square by 2m d square by dr square of UEL plus l into l plus 1 into h cut square by 2m r square plus v of r UEL of r is equal to EUEL of r. Then we coupling this with the fact that the spherical harmonics are separately normalized, so that the overall normalization condition becomes 1 is equal to integral r square into dr into r star el of r, or el of r is equal to integral dr u star el of r u el of r. From the above equation, we can some substitutions and arrangements apply. We get the substitution is that put UEL of R by R in the place of REL of R, and U star EL of R by R. By R comes from equation number 4. So, in place of R star EL of R, then we get 1 is equal to integral r square dr, integral r square dr r star el of r, or el of r is equal to integral dr u star el of r u el of r. Then our final equation, so we see that UEL of R can be interpreted as a wave function in one-dimensional for a particle moving in an effective potential. So we can write effective potential VE of R is equal to central potential V of R plus L into L plus 1 by h cut square by 2m r square, which is already derived from this equation. Hence proved. Okay.